we're going to numerically solve the IVP problems and plot our results for our TC and our TC equaling 290 and 305 for our constantly stirred tank reactor, and then explain the oscillatory behavior for our TC is equal to 305. So to start off, we have our numpy side by integrate subplots, and then we have a lot of givens here. Our flow rate in, our initial concentration, our initial temperature, our volume, the density of water, our C, our negative heat of reaction, it's negative, so it will fit better into our equation later. Our ER for calculating our KCA, our initial K, our UA, the heat transfer coefficient, our initial concentration in the tank, our initial temperature, again, but I had that twice, never mind. But our TCA, which will be our first instance, and then our TCB for our second one, and then we'll have this run for 10 minutes. So to start off, define our function, our CSTR, we'll call it CSTR1 as a function of t and our vector. And that vector will be equal to our concentration and our temperature. And we'll start off by getting our KCA, which will be equal to our initial reaction rate times our concentration times NP.HP of our negative ER divided by T. Then we'll move on to our change in concentration, which will be equal to our flow rate, our initial concentration minus our concentration. Then we will divide that by the volume again, and then minus KCA. Move down to our change in temperature, which will be equal to our flow rate times our temperature, is that CA? So our initial temperature minus, or our temperature coming in minus our temperature going out, divided by the volume, and plus the heat coming from the reaction because it's exothermic. So our negative heat of reaction times our rate of reaction, KCA, and this will be divided by our C and divided by rho, the density of water here. And subtracted from this will be our heat transfer to the jacket times our temperature minus our TCA for our first instance. This would be divided by C, rho, and the volume. Make sure that works so far. And then we'll have this return our change in concentration and our change in temperature. All right, and then we'll copy this down, make this our second scenario where we have our TCB. The rest should be okay to leave the same. All right, we'll move on again. So our res1 will be equal to solve IVP of our CSTR1 to there you go, from 0 to T end. Our initial values here will be CA0 and T0. Dense output equals true. Our method will be RADU for better accuracy. Is that, which one is having a problem here? It's not callable. CAIC DC. All right, it took me a little while to see it, but it's just a simple mistake here. I forgot to multiply variables, I guess in this case constants, in front of parentheses. And if we run both of these, I'd imagine, all right, we're all good. Now we'll move on. We just need to do this once again. We'll call this our res2. This will use our CSTR2. And I don't think, we'll see how this works. So we'll move on. We'll need to make our t-plot. So our t-plot is np.lin space from 0 to t end, and we'll do 1,000 different points. Now we can get our CA1 and our T1, which will be equal to our res1 dot solve of our t-plot, and then our CA2 and our T2 will be equal to our res2 dot solve of our t-plot. That works out. From here, we should be able to just make our graphs. So they make subplots, rows equal 2, columns equal 2, big add, scatter. Our x will be our t-plot, our y will be our CA1, mode is lines, name is CA1, this will be in row 1, column 1, and we should just be able to take this, send it down a few times, and make some adjustments. So the next one will be T1, CA2, T2, change the names quick, T2, T1, CA2, oh, fix this, row 2, row 2, column 2, column 2, and we'll see what this does. All right. So as you can see in our first situation, it comes to a steady state of about a concentration of 0.95, and then our temperature will also come to a constant of around 312. But in our second scenario, we have oscillatory behavior here. And that is due to the fact that the temperature is reliant on the reaction taking place. However, as the reaction takes place faster and makes more heat, the concentration will go down because it's using up more than what's coming in. So when we start off, our reaction will begin, generating more heat, causing the reaction to go faster, causing the total concentration in the tank to go down. And once it gets to this point, the reaction can no longer happen fast enough to keep the temperature increasing. So the temperature will begin to fall, slowing down the rate of reaction, letting the concentration build back up. And eventually, once it gets back up here, there's enough for the heat will begin to rise again, causing the reaction to take place faster, going back down to a point in which it needs to slow down again, letting the concentration build back up, and it will keep oscillating like this pretty much indefinitely. All right.